Hello, I'm Dr. Leo DiDomenico, and I am developing a means to make optics software programmable by bending light electronically. It has many applications. However, in this presentation, I focus on a method for concentrating solar energy to create temperatures as high as 1500 degrees Celsius on a large industrial scale, with applications in smelting steel, manufacturing cement, recycling, and electricity generation. Intense solar heat represents an underserved niche market opportunity which can provide revenues of more than $100 billion per year, and a chance to help overcome the growing pain of global warming by eliminating 25% of greenhouse gases while creating energy independence. Today, even the best solar power plants are too inefficient to handle these jobs at the scale of thousands of land-intensive facilities. Tragically, today's heliostats can waste more than 90% of the incident sunlight to the ground. We need something better, a different approach, a new kind of optics. Therefore, I'm creating an alternative to conventional mirrors and lenses, a low-cost, unprecedented, solid-state light steering technology that can collect all of the incident sunlight falling on a large area, which is 10 times more energy harvested than today's solar plants of the same size, and then focus it to generate very high temperatures directly. I have self-funded 16 years of full-time research at the intersection of physics, chemistry, optics, the electrodynamics of materials, and surprisingly, even to me, the mathematics of general relativity, all revolving around one unconventional question. How can I program the refractive index of a material to make any optical device? And I have found an answer to that question. I call it optometaphoresis, which means optics changed by migration of nanoparticles. I've discovered that trillions of nanoparticles suspended in a liquid colloid and subjected to non-uniform rotating electric fields can slowly change their orientation by diffusion and therefore modify refractive index by a process called dielectrophoresis. At each point in its path, light bends towards the higher refractive index. The initial orientation, the direction, and rate of rotation of nanoparticles changes the light's trajectory. This is similar to the way the path of an object through an asteroid field is deflected by the local gravity of the asteroids. This principle can be applied to create a paper-thin, directed energy solar array that dynamically concentrates sunlight in a solar power plant. There are three parts to optometaphoresis. First, a specially synthesized colloid provides a controllable anisotropic material. Second, a mathematical recipe orients the particles in the colloid. Third, electronics imposes the needed spatial structure to the colloid using forces and torques based on dielectrophoresis. The demonstration of a directed energy solar array is complex. Therefore, I decided to start with a small proof of concept in which a light beam is switched between two distinct angles. A test fixture was designed and built to hold a colloid sheet 100 microns thick while the electric field is applied with specially designed oscillating voltage and current electrodes. My biggest technical challenge is synthesizing the colloid, which is difficult but has been done by other researchers in a different context. So I am confident it can, in time, be done again. I start with commercial titanium dioxide nanoparticles, which typically arrive stuck together in clumps. Sophisticated processing comprising sonication, centrifugation, evaporation, and chemical stabilization are then used to separate the particles, increase their concentration, and keep them separated permanently. Then, dynamic light scattering is used to measure average nanoparticle size and show that particle size and concentration are changing in a controlled way. Dynamic light scattering tests have shown progress in controlled separation, but most particles still need to be reduced in size further and the desired particles stabilize from snapping back together again, as can be seen in these graphs. A hard-to-obtain, specialized nanoporous filter is needed for the next stage, and procuring it will delay the colloid demonstration by 1 to 2 months. So in the meantime, I've conducted a parallel experiment using liquid crystals to create the anisotropic fluid. The liquid crystals have some optical and electrical properties similar to the colloid. Unfortunately, the experiment could not be completed in the time given due to delays in arrival of equipment, though I continue to press forward even now. Next steps include teaming with Sandia National Laboratory to further assist in synthesizing the needed colloids and a demonstration of full angular scanning of the light beam. This is an exciting project, and I hope it will continue. Thank you very much.